Let's say we had 64 college basketball teams, and we wanted to know which one of those teams is the best. How can we do that? Well, your first thought might be have each of the teams play each other, and whoever wins the most games, that's the best team. But that would take 2016 games, so I bet we could do better. Let's strategize a bit. Maybe we could take the 64 teams and split them up into two groups of 32 teams. We could find the best out of those 32 teams and have them play each other, and whoever wins that game, he's the best of all the 64. Yeah, that works, but now we're kind of stuck with the same problem because, well, how do we find the best of the 32 teams? It's just the same problem on a smaller scale. But if it's the same problem, we can use the same strategy. Let's split the 32 teams up into groups of 16 teams and do the same process. We can keep doing that. To find the best of 16, we have to find the best of two groups of 8, and then we have to divide those up into 4, and then those up into groups of 2. But once we get there, we can easily find the best of 2 teams. We just have them play each other. And in that way, we can find the best of the 64 teams, just by continuing to subdivide our problem. So what we're doing here is using a method called recursion, which is when you have some large-scale problem, and in order to solve it, you split it up into smaller subproblems that are easier to solve. And using those solutions, we can find a solution to the bigger problem. This might be all abstract, so I'll give you an example. Let's say you were trying to find, like, factorial. You were trying to write a factorial function. Factorial, just to remind you, is like, if you have 5 factorial, you would do 5 times 4 times 3 times 2 times 1. So you just multiply all the numbers up to whatever n is. Like, so let's say we were trying to find 100 factorial. That would be multiplying 100 numbers together. I bet there's an easier way to do it. How about we just do 100 times 99 factorial? That's the same thing. That's the same thing as 100 factorial, so that works. But, okay, wait. How do we find 99 factorial? Same strategy. 99 factorial equals 99 times 98 factorial. Okay, but then we don't know 98 factorial. Yeah, you see where this is going. We're just going to keep going down the chain. 33 factorial equals 33 times 32 factorial. Eventually you'll get down to 10 factorial equals 10 times 9 factorial. And you keep going down until you get to 0. And at 0, you can say 0 factorial equals 1. That's something that you know. Okay, cool. Finally, we have a concrete number. So we can take that 0 factorial and move one step up. 1 equals 1 times 0 1 factorial equals 1 times 0 factorial. Okay, cool. So that means 1 factorial equals 1. So we're going to keep moving up the chain until eventually we get to back to 100 factorial. It'll come to a point where we'll know 99 factorial, and we just have to multiply that by 100, and we get our solution, which is, have it written down somewhere. Or maybe I googled it. Yeah, 9.33 times 10 to the 157, which is a huge number. Okay, so let's think about what that would mean in terms of computer science. Like if we were trying to write a factorial function. Here, I wrote it. Factorial of n. Really, what you want to do is return n times factorial of n minus 1. Or if you're already at 0, you can just return 1. 0 is, when n equals 0, that's a special case. It's called our base case. The base case is where you can't really subdivide the problem into any smaller subproblems, so you just have to return an answer. And that's what we do here. We get to our base case. If n equals 0, return 1. Cool, so once we return 1, it'll go back up to the function factorial. It would be 1 times factorial of 0, which returns 1, and then it goes back up to factorial 2. Yeah, you get the point. So let's take a look at it, like how we would do factorial 5. If we call the function factorial 5, well, does n equal 0? No? Then let's return 5 times factorial of 4. Alright, what's factorial of 4? Is 4 equal to 0? No, of course not. So we return 4 times factorial of 3, so on until eventually we get down here to factorial of 0. Is n equal to 0? Yeah, you bet. So we can just return 1. And there we can just multiply that by 1 to get factorial of 1, which we can multiply by 2 to get factorial of 2, yada yada yada, until we get to factorial of 5, which is 120. Just a few terms related to recursion. Let's see, tree recursive. That's when a recursive function calls itself more than once, multiple times. Like if we had a function find best team, and we gave it an array of 64 basketball teams, that function would call find best team on 32 Eastern teams or whatever, and it would call it again on the 32 Western teams because it had to find the best of the two subgroups. So that's tree recursive, a function that calls itself multiple times. But linear recursive function, that's a function that just calls itself once, like our factorial function. Our factorial function is linear recursive because it has its base case, yes, but in the recursive step, it only calls factorial n-1. It doesn't call factorial more than once within the function. Okay, so that's linear recursive, and then a subsection of linear recursive is tail recursive, which is when the recursive call is the very last thing the function does. So basically, if you have a function like do this, the last line of the function should be return do this of whatever subgroup you're doing. So though the factorial function that we wrote is it is linear recursive. It only calls itself once. It's not tail recursive because after it calls itself, it has to multiply that result by n and then return it. So it's not the very last thing the function does. It's the second to last thing the function does. And okay, so that's a short description of recursion. If you have any questions, ask me, I guess. There's comments below. Thank you.